All right. I did not expect this from Gemini. I uploaded a PDF just for fun to see if Gemini could really summarize the PDF. And what came out sounded like a full blown podcast. It's really insane. Perfectly structured, emotionally tuned, and way too good to be AI generated. I don't even know what to say. Take a listen. Trust me, you're not ready for what it can do.
Totally bogged down.
Exactly. You want to understand complex stuff fast. And that's precisely what we're doing today on the deep dive. We take sources this time. One's provided by you, our listener, and we sort of act as your guides. We pull out the really valuable insights.
And our subject today, well, it's fundamental to computing. Data structures and algorithms.
Right.
Our main source here is Data Structures and Algorithms Made Easy by Narasimha Karumanchi.
Good one.
And this is really for you, the learner. That's how we're thinking of you. Someone curious, wants the knowledge without the overwhelm, likes things clear.
Yeah.
This is for you.
Absolutely. So our mission, our goal today, is to pull out the essential principles, how data gets organized, how we figure out if problem-solving methods are any good. Efficient, I mean.
Yeah, all from this book.
Yeah. We're talking basic building blocks, categories, comparisons, the absolute core of how computers handle information. So let's jump in. Let's unlock some useful stuff.
Right, let's start at the very beginning. Think back to basic math, like algebra.
Sure.
You'd see something like x plus y equals 10, right?
Mm-hmm.
X and y, they're variables. They just hold values.
Oh, just for numbers, yeah.
Exactly. And chapter 1 of the book kicks off right there. In programming, variables do the same thing. They're placeholders for data. It sounds basic, but it's super crucial.
Right, okay. And it builds from there, I assume? Like in math, you have whole numbers, decimals,
Yep.
different types of numbers?
Precisely. Programming has data types. The book calls them classifications of data.
Classification
You've
types.
got system-defined ones, the
Yep.
basics like integers, floating point numbers, primitive types.
Like int, float, that kind of thing.
Yep. And then user-defined types, things like structures, classes. Now here's the key thing. These types aren't just labels. They actually tell the computer how to store the data in memory.
Ah, so it relates to the actual bits and bytes.
Directly, yeah.
Yeah.
Telling the computer the type up front, it just makes your code way clearer and often more efficient too.
Okay, that makes sense. So variables hold data, types tell us what kind of data. How do we organize it all?
That's the next step, data structures. The book defines them as basically methods for storing and organizing data efficiently. That's the goal, efficiency.
Right.
And it groups them neatly. Linear structures where elements are in a sequence. Think linked lists, stacks, queues.
Like beads on a string, sort of.
Kind of, yeah. And then nonlinear structures, things are more connected, maybe hierarchical, trees, graphs, that sort of thing.
Okay, I'm picturing my bookshelf, piling books randomly, no structure, alphabetical, that's linear,
Good analogy.
and maybe a family tree, that feels nonlinear.
Exactly. And why bother organizing?
Yeah.
It's all about efficiency. The right structure makes getting to your data, changing it, much, much faster.
So structure matters for speed. Got it. What about what these structures can actually do?
Right. That brings us to ADTs, abstract data types. The book explains them as the data structure plus its allowed operations.
Okay.
But here's the important bit.
Mm-hmm.
An ADT tells you what it does, not how. It's like a blueprint.
Ah, okay. So like a stack ADT.
Mm.
You know it's last in, first out, LIFO.
Yep.
And you can push stuff on, pop stuff off, but you don't need to know how the push or pop works underneath.
Exactly. That's the abstraction. Same for queues, first in, first out, FIFO. The ADT defines the behavior, the interface, not the internal mechanics.
Okay, so ADT is like my shopping list app. I know I can add items, check items off. That's the what. I don't need to know the code behind the scenes, the how.
Perfect analogy. So we have data, we have ways to organize it. How do we process it?
Algorithm.
Bingo.
Algorithm.
The Kriyomanchi defines an algorithm as a step-by-step,
Yeah.
unambiguous procedure for solving a problem. Unambiguous is key.
Right. Needs to be clear instructions.
Yeah, he uses the analogy of making an omelet.
Yeah.
You follow a recipe, a specific sequence of steps. That's your algorithm.
Okay, makes sense. But surely there's more than one way to make an omelet or solve a programming problem.
Absolutely. And that leads straight into why we need algorithm analysis.
Ah, comparing the recipes.
Kind of.
Mhm.
The book uses traveling between cities. Different routes, different times, maybe different costs. Algorithm analysis helps us compare different approaches, figure out which one is most efficient.
Efficient meaning.
Primarily, how much time it takes running time, and also how much memory it uses. Those are the two main criteria.
Okay. So how do we compare them fairly? You can't just time it on your laptop, right? Mine might be faster than yours.
Exactly. The book stresses that. Execution time varies too much. Even counting lines of code isn't reliable.
So what do we do?
The goal, Karamanchi explains, is to express the running time as a function of the input size. We usually call the input size n.
Okay, like the number of items in a list we're sorting.
Precisely. Or maybe the number of nodes in a graph. It depends on the problem. But expressing time in terms of n, like fn, lets us compare algorithms more generally, regardless of the specific computer or minor coding differences.
Okay, Fn, a function of the input size. How does that help us compare?
Well, the crucial idea here is the rate of growth. How quickly does that function, f at n, the running time, increase as it gets bigger and bigger?
Ah, how does it scale?
Exactly. The book uses a nice analogy. Imagine buying something with a small fixed delivery fee plus a cost per item. If you buy loads of items, that fixed fee becomes pretty insignificant, right?
Yeah, the per item cost dominates.
Same idea with algorithms. When it gets really large, we focus on the part of the function fn in that grows the fastest, the dominant term.
So if the time is like n to the power of 4 plus some smaller stuff.
Like n4 plus 2n2 plus 100n plus 500, yeah.
For a huge n, that's basically just going to behave like n4.
Pretty much. The other terms get swamped. The book even has a diagram showing common growth rates: constant, logarithmic, linear, n log n, quadratic, exponential. It helps visualize how steeply the time increases.
Okay, so we focus on the fastest growing part for large inputs. Makes sense. Now, the book mentioned different types of analysis: best, worst.
Right. Best case, worst case, and average case. Worst case is the scenario where the algorithm takes the absolute longest.
The upper limit.
Yep. Best case is the shortest time possible.
Lower limit.
Uh-huh. And average case is, well, what you'd expect on typical inputs, averaged out. The book gives this relationship: lower bound, average time, upper bound.
Okay. And how do we talk about these bounds formally?
That's where asymptotic notation comes in. It's the standard mathematical language for this.
Right, I've seen these. Big O, omega.
Exactly. Big O, omega, and theta. Big O notation gives us the upper bound on the growth rate.
Maximum rate.
Yes. The maximum rate, the running time, grows for large n. Formally, it involves finding constants, c and n, such that for all input sizes in bigger than n, the running time f in n is less than or equal to c times some function gn. We say fn is ogn.
Okay, that sounds a bit mathy. What's the intuition?
The intuition is it tells you the worst that can happen, growth-wise. How bad can the performance get as the data scales up? This is super important for real-world stuff, predicting bottlenecks.
Got it. So if something is ON, like that 3n plus 8 example you mentioned.
Yeah, fn 3n plus 8, we can say it's on because if you pick c of 4 and n0, 8, then for all n greater than or equal to 8, 3n plus 8 is definitely less than or equal to 4n.
Okay. And the book said those c and n NO values aren't unique.
Right, there can be multiple valid choices. The main point is finding some pair that works to show the upper bound relationship holds for large enough n.
So big O is the upper limit on growth. What's omega?
Omega is the flip side. It gives the lower bound, the minimum rate of growth.
The best it can do, growth-wise.
Essentially, yes. Again, there's a formal definition with c and n0, but this time cgn has to be less than or equal to fn for large n.
Okay.
The book shows fndn 5n2 is nn2, and it also shows how to prove something is not an omega. Like 100n plus 5 is definitely not nn. It just doesn't grow fast enough.
So big O is pessimistic, omega is optimistic about the growth rate anyway.
It's a good way to put it.
What if they met? What if the upper and lower bounds kind of meet?
Ah, that's theta. The book explains theta means a tight bound. The growth rate is sandwiched between two multiples of the same function.
So C1GN is less than FN, which is less than C2GN.
For large enough n, yes, that's the formal definition. The example given, 5n3 plus 2n2 plus 4n3 plus 1, that simplifies to basically one constant time growth.
Meaning it doesn't really get slower as n increases.
For large n, its growth rate is constant, yeah. Doesn't depend on n in the limit.
Okay, big O, omega, theta, which one do people use most?
Karamanchi points out that in practice, especially later in the book, the focus is often on big O.
The upper bound.
Yeah, because knowing the worst case performance is often crucial. It gives you a guarantee. But theta is great when you can establish it because it's very precise. It tells you exactly how the algorithm scales asymptotically.
And why call it asymptotic analysis?
Good question. It's because we're looking at the behavior as n approaches infinity. as the input gets really, really big.
Like asymptotic curves in math that get closer and closer.
Exactly like that. We're approximating the function's behavior at the limit for large values.
Yeah.
We generally ignore how it behaves for small inputs.
Okay, so how do we actually do this analysis on code? Does the book give tips?
It does. Guidelines for common structures, like a simple loop that runs n times, usually O(n).
Makes sense.
Nested loops often multiply, so a loop inside a loop, both run in n times, likely O(n).
Okay.
Consecutive statements, you just add their complexities, and the biggest one dominates.
And if then else.
For worst case, you take the complexity of the condition test plus the complexity of whichever branch, the then or the else, takes longer.
Got it. What about that logarithmic one, O log n? That seems less intuitive.
Yeah, O log n often pops up when an algorithm cuts the problem size down significantly in each step, like dividing it by 2 or by 3, some constant factor.
Having it repeatedly.
Right. The book gives the example of a loop where the counter I is multiplied by 2 each time. It reaches n much faster than just adding 1. Binary search is the classic O log n example. You throw away half the search space each time.
Okay, that makes sense now. It grows much slower than linear.
Much slower. And the book also lists simplifying properties for these notations, ways to combine them, like rules for adding complexities or multiplying them, handling constants, helps clean up the analysis.
Like algebraic rules for growth rates?
Pretty much. And there's a handy list of common logarithms and summation formulas you often need.
Math tools for the job. Okay. What about those algorithms that break problems down? Divide and conquer.
Yes. The master theorem. A really powerful tool for analyzing divide and conquer algorithms specifically.
How does it work?
These algorithms break a problem of size n into A subproblems, each of size mb. Then they solve those recursively and combine the results. The combining step takes some time, say f and n.
Okay, so Tn equals ATNB plus Fn. That's the recurrence.
That's the general form, yes. The master theorem gives you 3 cases based on how Fn compares to n log big. Depending on which case applies, it tells you the overall time complexity Tn directly.
Wow, like a formula for the answer.
Almost. And Karamanchi really hammers this home with problems 1 through 20. Lots of examples worked out using the theorem.
Practice applying it.
Exactly. And crucially, he also shows when it doesn't apply. You need to recognize the limitations.
Good point. Are there other types of these theorems?
The book briefly mentions one for subtract and conquer recurrences. That's when the problem size reduces by a constant amount, like Tn1, plus something, not divided by a factor.
Okay.
And a variation on the main master theorem, too.
But what if none of these theorems fit your algorithm's recurrence? Are you stuck?
Not necessarily. That's where the method of guessing and confirming comes in.
Sounds hopeful.
It's more rigorous than it sounds. You make an educated guess for the solution, say O(n) log m, and then you try to prove it mathematically, usually using induction.
So you guess, then prove or disprove.
Right. The book walks through Tnn, 2Tn2 plus n log n, show it's too big, guess O(n), show it's too small.
Bracketing the answer.
Exactly. Which points towards a likely, more complex answer, O(n) log n, by proving the upper and lower bounds around it.
Clever. Okay, one more analysis type mentioned was amortized. How's that different from average case?
Good question. Amortized analysis looks at the average cost per operation over a sequence of operations. Average case often makes assumptions about input probability. Amortized doesn't.
So it's about the average cost over time, not assuming random inputs.
Right. The motivation is sometimes you have an operation that's really expensive, but it happens rarely. Amortized analysis averages that expensive cost over the more frequent, cheaper operations.
Like your garden analogy from before, lots of quick watering days average out the occasional heavy weeding day.
Exactly. The book uses finding the case smallest element repeatedly. Sorting the array once is expensive, maybe O(n) log n.
But then finding the kth element is super fast, O(1) maybe?
Right. Amortized analysis captures that overall efficiency. The expensive sort pays off over many fast lookups.
Got it. And the chapter wraps up with lots of problems.
Loads of them. Problems 21 to 65, analyzing recurrences, code snippets, comparing function growth rates, conceptual questions. Really solidifies everything from chapter 1, covers all sorts of complexities, O(n), O log n, O(n), O(n)2, even O(2n).
Okay, that was a deep dive just into chapter 1. Ready for chapter 2, recursion and backtracking.
Let's do it. Chapter 2 starts simple. Recursion is just a function calling itself.
Like Russian dolls.
Kind of. The core idea is solving a problem by breaking it into smaller, identical subproblems. But crucially, you need a base case.
The smallest doll. The point where it stops calling itself.
Exactly. Without a base case, it calls itself forever. or until you run out of memory.
Why use recursion then? Seems potentially risky.
Well, Karamoachi points out the advantages. Recursive code can be really short, elegant, easier to write and understand sometimes, especially for problems that naturally break down recursively, like sorting or searching tree structures.
But the downside?
There's overhead. Each function call takes a bit of time and memory on the call stack. If it goes too deep, you can get Stack Overflow errors.
Ah, okay. How does it compare to just using loops? Iteration.
The book draws a clear comparison. Recursion stops at a base case. Iteration stops when a loop condition is false. Recursion uses stack memory for each call. Iteration usually uses constant memory.
So iteration is generally more efficient.
Often, yes, in terms of time and especially memory. But recursion can be clearer conceptually for some problems. The book notes you can almost always convert recursion to iteration using an explicit step data structure if needed.
Okay, so key takeaways on recursion. Need base case, need recursive case, ensure termination, often less efficient than loops, but good for certain problems.
You got it. And the book lists common examples: Fibonacci, factorials, merge sort, quicksort, binary search, tree traversals.
Flowers of Hanoi.
Yep, that classic puzzle is a prime example of recursion. Moving N1 disks, moving the largest, moving N1 disks again. Beautifully recursive.
The book even uses recursion to check if an array is sorted.
It does. Simple idea. Check the first two elements, then recursively check the rest. But it highlights the trade-off. ON, time, but also ON, space, because of the recursive calls stacking up.
Right, the memory usage. Okay, what about backtracking? The book calls it an improvement over brute force.
Yeah, it's a smarter way to search for solutions. You explore possibilities step by step. If a path looks promising, you keep going. If it's a dead end or violates rules,
You backtrack.
exactly. Undo the last choice and try a different one. Think of exploring a maze.
Or a decision tree. You prune the branches that won't work.
That's the key idea. Pruning the search space makes it much faster than trying every single combination blindly.
What kind of problems use backtracking?
The book lists generating binary strings, carry strings, the n-queens puzzle.
Placing queens on a chessboard so they don't attack each other?
Right. Also knapsack problems, finding Hamiltonian cycles in graphs, graph coloring, lots of combinatorial search problems.
Does it show actual backtracking code?
Yep. Recursive algorithms for generating all binary strings of length, that's O to N complexity, and all carry strings, O carry N, shows how it explores the whole space.
Exponential. So it can still be slow.
Often, yes,
Yeah.
but way better than unguided brute force. It also tackles finding connected cells of ones in a grid.
How does that work?
Start at a 1, recursively explore all 8 neighbors. If a neighbor is 1 and not visited, mark it, add it to the count, and explore its neighbors. Systematically finds the whole connected region.
Okay. And the chapter ends analyzing another recurrence.
Yeah, Tn equals 2Tn1 plus 2n, uses the recurrence tree method again, shows it comes out to On2n, reinforces the analysis techniques.
Okay. Chapter 3. Linked lists. Let's dive in. How does the book define them?
As a linear data structure, but elements aren't necessarily next to each other in memory. They're connected by pointers.
Nodes containing data and a pointer to the next node.
Exactly. Each node points to the next one. The very last node points to NULL, signifying the end.
And they're dynamic. They can grow and shrink easily.
That's a key advantage. Unlike arrays, where you often have to decide the size up front, linked lists are often more memory efficient if you don't know how much data you'll have.
What are the main things you do with a linked list? The ADT operations.
Karamanche lists the main ones. Insert and delete nodes.
It makes sense.
And auxiliary ones. Delete the whole list, count nodes, find the nth node from the end, which is a classic problem.
Why use them instead of arrays then? Arrays seem simpler sometimes.
Good question. The book tackles that head-on by comparing them. Arrays give you that instant access, right? O1, time to get element I.
Because you can calculate the memory address directly. Index times element size plus the start address.
Exactly, super fast access. But arrays have downsides? Fixed size, usually.
You have to guess how big it needs to be.
Right. They need one continuous block of memory. And inserting or deleting in the middle, that's slow. You have to shift everything after it.
OS, for insertion deletion in the middle.
Yeah. Dynamic arrays help with resizing, but that shift cost is still there.
Correct. So linked lists shine where arrays struggle. Need dynamic size, frequent insertions deletions, especially near the beginning. Linked lists are often better.
Because inserting deleting is just changing a couple of pointers, right? O1 time, if you're already at the right spot.
That's the catch. Finding the spot takes time, but the insertion deletion itself is fast. But linked lists have their own issues.
Like accessing element I. You have to walk the list from the start. Yep, ON. Access time. No random access. Also, poor cache locality because nodes can be scattered in memory. And the pointers themselves take up extra space.
Trade-offs everywhere. The book has a table comparing them.
Yes, a very useful comparison table. Linked lists versus arrays versus dynamic arrays. Sums it all up.
Okay, let's get specific. Singly linked lists, one pointer per node.
The basic model. Each node has data and an X pointer. Last one points to NULL.
And the book walks through the operations. Traversal, insertion, deletion.
Meticulously. Steps and logic for traversing. Inserting at the beginning, end, or middle, with time and space complexity for each, and how to delete the whole list safely.
Oh, okay. What about doubly linked lists? Two pointers.
Yeah, each node has a next pointer and a previous pointer.
Ah, so you can go backwards too.
Exactly. That's the big win. Makes some operations easier. Like if you have a pointer to a node, you can delete it in O1 time because you can easily access its previous node using the prev pointer. You don't need a separate pointer to the predecessor like in singly linked lists.
Clever. But downsides.
More memory per node for that extra pointer. And insertions deletions are slightly more complex. You have to update both next and prev pointers correctly. Again, the book details all the insertion deletion scenarios.
Okay, singly, doubly. What's next? Circular.
Circular linked lists. The last node's next pointer doesn't point to NUL.
It points back to the first node, creates a loop.
Precisely. You need to be careful traversing so you don't loop forever.
How do you know when you're done?
You usually keep track of the starting node and stop when you get back to it. The book covers counting nodes, printing, inserting at front end, deleting first last, and mentions uses like round-robin scheduling.
Interesting. Are there weirder linked lists?
Well, the book introduces a memory-efficient doubly linked list using XOR.
XOR, the bitwise operation. How does that work?
Instead of storing separate next and prev pointers, each node stores a single iterative field. This field holds the XOR of the previous node's address and the next node's address.
Okay, how does that help me move?
Using XOR properties. If you know the address of the current node and the address of the previous node, you can XOR them with the protective field to find the address of the next node, and vice versa.
Whoa, so you can navigate both ways with just one pointer field?
Effectively, yes.
Yeah.
Saves memory, but the pointer math is definitely trickier.
Mind-bending. Okay, what else? Unrolled linked lists.
Yeah, these try to improve cache performance. Instead of one data item per node, each node, or block, holds multiple data elements, like a small array within the node.
So fewer nodes overall, more data packed together.
Right. These blocks are then linked together. It's a hybrid approach. Might improve search time compared to regular linked lists, maybe closer to O or N, because you jump between larger blocks.
But insertion seems complicated if a block gets full.
It can be. The book mentions a shift operation might be needed to rearrange elements within or between blocks to maintain size limits. It discusses the speed, cache, and space advantages over standard lists.
Okay, one more. Skip lists. Sound fast.
They are. They're a probabilistic alternative to balanced trees like AVL or red-black trees.
Probabilistic.
Yeah. Imagine a basic sorted linked list. Now add another layer of pointers above it where some nodes have an extra pointer that skips over several nodes in the base layer.
Like an express lane.
Exactly. Now add more layers, with pointers skipping even further. The number of layers or pointers a node has is determined randomly when it's inserted.
So searching can jump across large parts of the list using the upper layers.
Precisely. It gives you O log and N, average time for search, insertion, and deletion. Much better than ON for regular lists.
Wow, that's clever. Like multiple levels of express lines.
A good way to think about it. The book shows diagrams and compares performance.
Okay. And chapter 3 also ends with problems.
Yes. Problems 2 through 11. Finding nth from end using different methods, brute force, hash table, 2 scans, 1 scan with 2 pointers.
That 2-pointer trick sounds useful.
It is. Then cycle detection finding loops. Brute force fails, hash table works but uses space. Sorting doesn't really work here.
So what's the best way?
Floyd's cycle finding algorithm, the tortoise and hare. 2 pointers, 1 slow, 1 fast. If there's a cycle, they'll eventually meet. ON, time, O1 space. Very elegant.
The tortoise and the hare. I like that. And it can find where the cycle starts, too.
Yes. Problem 11 extends it to find the start node, though the details might be just beyond what we cover fully here from the source ending.
Okay, incredible. We've covered a huge amount just from those first 3 chapters.
Absolutely. So just to wrap up this deep dive, we've seen how fundamental data representation is, how data structures give us organization, and how that impacts efficiency.
Right, and ADTs as the blueprints, algorithms as the recipes.
And crucially, how to analyze algorithm efficiency using asymptotic notation big O omega theta to understand how they scale.
Yeah, understanding that rate of growth seems key. We also looked at recursion and backtracking, powerful but sometimes costly techniques.
And then the whole world of linked lists opened up. Singly, doubly, circular, XOR, unrolled, skip lists, each with its own strengths and weaknesses.
Definitely a lot of trade-offs to consider. It's clear how choosing the right structure is vital for performance.
It really is. These concepts, they seem abstract, but they have very real consequences for how well software performs. Hopefully seeing the connections was helpful.
I think so. And for you, our listener, the learner, we really hope this journey through Karamanchi's explanations has given you a solid, clear understanding without feeling too overwhelming.
Yeah, we aimed for the core insights, using analogies to make it stick.
So here's a final thought for you to chew on. Now that you've got this foundation in analyzing efficiency, think about the real world. What specific problems out there could really benefit the most from picking just the right data structure and algorithm?
And why? What makes you think that particular structure or analysis is so crucial for that problem?
Great question to ponder. And hey, if you've got your own set of sources, maybe a book or some articles on a topic you're curious about, send them our way.
We'd love to do another personalized deep dive just for you.
Absolutely. Until next time, keep thinking deeply and keep learning.